How's it going, guys? I think we're live this evening. First thing I want to look at is this JL Audio 500/1V2. Quite an old amplifier now, quite an old circuit now. Right, so what do we have? We have, burned power supply FETs, as we can see over here. Got a very charred, toasty one there. Now the FETs that these come with as standard are IRFZ 44V. It's not super critical what we use in place here, and I'm quite surprised actually. So the output section, this is actually using IRF 540s, not IRF 540N or IRF 540Z or anything like that. It's using straight up old-fashioned 540s, and the differences in the suffix there with the letter on the end, whether it's a 540, 540N, 540Z, it's to do with the die size, and also what they're going to be best suited for. So 540s on their own like this are usually seen more in class AB amplifiers. So the actual part is the same and the specifications are the same, but the power dissipation, or very similar anyway, but the power dissipation will be quite a bit different. The smaller the die size, the better it is for switching applications, but the less power it can actually get rid of, the less heat energy it can get rid of as heat to the heatsink, because the die is smaller. So it can't get rid of that energy. That power dissipation is much lower. So although you might have three parts, the 540, 540N, 540Z, for example, with very similar current ratings, so that they can take the same amount of current for like short periods, without damaging the silicon or the die inside, or anything like that. But the actual power dissipation of the faster switching parts and the smaller die parts is much less. So usually, and also that they run more efficiently as well, so usually in the Class D amplifier you'll see the smaller die parts. However, in this case we've actually got the large die part. Here's the PCB for the 500/1V2, and the actual revision of this board, because they go through lots and lots of different revisions. The revision of this board is revision 11, so pretty high up actually. It's one of the newer, more later ones. And we can see here that we've got the 4 output FETs. We've got 2 high side and 2 low side over here. Sorry, yes, one high side and 1 low side per half bridge. It's basically a 2-channel amplifier in internal bridge. So yeah, that's one channel, high low. That's the other channel, high low, and they're 180 degrees flipped from each other. Single positive. It's basically a Brazilian. This is the exact same shit that's going on inside a Brazilian 4-bridge amplifier. It's exactly the same. It's just JL Audio did it years before, and just the circuit looks like a different layout, but it's a very similar circuit layout, even very similar drive circuit. In fact, it's pretty similar. The JL does have some other clever stuff up its sleeve in terms of protection and turn-on style and stuff like that, but yeah, the basic concept is the same. It's a full bridge amplifier with a single positive rail voltage, just like a Brazilian. So we know that we have dead output FETs and dead power supply FETs, so we might as well just go ahead and desolder all the FETs from the board to start with. And these boards, just like the Rockfords that we were working on the other night, have pretty high thermal mass. So I'm going to go ahead and turn on the really big 200-watt soldering line to start with, just to save me wasting my time. And we're also going to preheat the board a little bit, just to get the board a little bit warmer. On the multimeter. That one's dead short, yeah. Okay, a couple of dead FETs then, yeah. I covered that in my video about the Taramps Smart 5. I explained about constant power amplifiers and how that you shouldn't be comparing them to amplifiers of the same power rating that are not constant power. Alright, all the FETs are out, so let's give this a little clean on the top here. So there's a couple of resistors here that look like they might be burned, but if the Mosfet only shorted from source to drain and didn't get a chance to send much or anything down the gate line, if it didn't really short to the gate, then these resistors that look black, that look burned, they may not actually be burned at all. It may just be covered in soot from the Mosfet that blew on top of it. So we can have a look and we can see 46 point, nice, dead on 47 pretty much. 46.7. So remember, these are 5% tolerance parts, so you will have some fluctuation between, they won't be exactly 47, they'll be 47 plus minus 5%, 46.1. Okay, cool. Let's check the drive transistors in here, see if these are shorted or reading low resistance at all. And this way round we settle on 598. Very similar to the other side. Yeah, they're all reading fine on the multimeter. So let's apply some power from the power supply now, and just make sure we have decent looking square waves. So all of our parts are reading within tolerance, which is cool. There we go. Slowly increasing duty cycle. Wow, very, very slowly increasing duty cycle. That's some of the slowest power up increases in duty that I've ever seen. The 1000/1s don't do it that slow, they do it very fast. They go like whoop straight away. That is very, very slow. 6.3, 6.4, that's correct. Yeah, that one's good. 6.4, 6.4, 6.4, and 6.4. So that's looking good. Now let's go ahead and have a look on the output section. So output section. Now to get the square waves present on all of these FET banks, you do have to short some pins like on part of the drive circuit output section, but I think if I remember rightly, you do at least get a little bit of square wave perhaps on at least one of these. Okay, so by the looks of it, we actually might have some output drive circuit fault because we've got something different on each side. So remember, this is a full bridge amplifier, so it's essentially two channels that are the same. So on one channel, okay, if I power the amp off and power it back up again, we have nothing and nothing on the gates and the source, etc. But on this channel here, we actually have 2.7 volts, which is, by the looks of it, always there, even with the remote turned off. And this one here we have 1.4 volts. So we do actually have a difference there. Around the output FETs we have a bunch of drivers and we have a bunch of resistors that can all fail when the output FETs short. Now when we got this amplifier in, we actually had one FET from each half here that was shorted, so it's not like one half has failed and the other's fine. So we don't know at this time which one it is that's the issue. But what we can do is we can confirm the resistance of all these resistors around here, because these will fail sometimes and go bad, preventing decent switching and decent operation on the output section. So over here we've got a 471. So that should read 470 on the multimeter. Let's have a look. What do we have? 459. That's probably going to be fine. We have a 240 by the looks of it just here. 234, yep, and 75, same as the other side. So the resistors all there are fine. There's also some more low value resistors in the middle here for the drive circuit. We've got a 47 ohm just here. That's correct. We've got a 47 ohm just here. That's correct. We have a 10 ohm here and also here. So they're all good, and these ones here, by the looks of it, we have 221, 210, sorry, 220, 220, 220, and this is a 289. That's a high value resistor. That's probably a pull down, so that's probably fine. Okay, all resistors seem to be reading fine in that area. Let's check the transistors and diodes now for shorts or low resistances, and we're going to read the resistance, so the diode mode reading of these drive transistors, because these can fail and go bad as well when the output FETs fail. So we're going to flip the board over so we get good access to their legs. 399, that's fine, that's fine. Fine, that's okay. We're looking basically for shorts. When these transistors fail, they just go dead short pretty much, or like 10 ohms or something. So either the output section is okay, even though we've got different readings, different voltages on them when we power the board up. I'm concerned. I don't think the power supply is actually, the output section is actually okay. We do have, yeah, we've got a 4427. So this right here, this chip is a driver for the output FETs. So let's just see what side it's driving. It could be driving both actually, because okay, so you're driving this 47 ohm resistor. That then goes off to here. There we go. So you're driving this side through a 47 ohm resistor. Now, so this one 4427 is driving both sides. Okay, let's have a look at the diode mode readings between the pads here on the Mosfet locations, because that will tell us a little bit about the drive circuit. So we've got 580 one way round, and we've got about 1000 the other way round. On that one, 1300 that way round, 600 that way round. These are all values that I would expect to see. 589, 598. About 1300, going to settle off at 1300. Yeah, these are all values that I would expect to see. So I'm not finding any cause for concern just yet. So it's giving me the confidence to actually install MOSFETs into this, and with MOSFETs in there, we'll be able to have a little bit of a further look and see whether it actually is fine, and whether we can take something away from this, that we don't get any pulses. From memory of working on these slash amplifiers, you do get little pulses when you first turn on the remote. So I haven't applied the remote yet. All I've done is just turn the power supply on to 12 volts. So we don't get any DC on any of these just yet. If I touch the remote one time, we get a little bump to DC, 1.4 volts here, 2.7 volts there, nothing and nothing. So I'm used to seeing either a couple of little pulses there, or the same on both sides. But the fact we've got a bit of DC one side, not the other, is a bit of a cause for concern. So for example, this MOSFET location here, we've got 2.7 volts on the gate, but on the source we've got nothing. On the drain we've got 1.8. So the MOSFET will turn on when the voltage from gate reference to source is higher. The gate is referenced higher than the source. If the gate voltage is higher than the source, up to a certain threshold voltage, the MOSFET will turn on. So at the moment this MOSFET would be turning on, provided that the MOSFET turns on with 2.7 volts. So let's actually see if that's the case. Right, let's find some of these then. We need some IRF 540s, and we can use 540, or we can use 540N or 540Z, because this is a switch mode application. What we might have to do, just for the purposes of the stream tonight, is actually whack in some 640Ns. They'll be close enough just to test the circuit, and then we can order some brand new 540Ns, I think, because I don't have any. Okay, so we haven't got any power supply fits in yet, so we're not getting any rail voltage. I was just really curious to see whether we had oscillation like we do with the other JL audios before the rail voltage is built. So we still have that DC there. It's not on the source leg still. In the output drive circuit, I'm not super confident. Actually, let's just see what the 4427 is doing in the middle here. We've got the drive chip 4427 just there. TC 4427E. It might be the same pin out as the IR version, but we just want to make absolutely sure we've got the right part. So VDD is pin number 6. 2 is the only pin with voltage on it at the moment, 3.6 volts. Sorry, 6 and 7, 2.7 volts. So we don't really seem to have VCC anywhere. So that chip isn't getting fed yet with any voltage, because we had the highest voltage we had was on pin 2, wasn't it? Pin 2 is in A. Now, that's weird. The highest voltage was in A. And then 6 and 7 we had the same voltage, which suggests that they might be shorted perhaps. So let's just have a look at the resistance between 6 and 7. Is that shorted? 541? Nope. Okay, let's just whack some power supply fits and see what happens. I don't think that this circuit is happy. I think we should have PWM on these output FETs, at least on a couple of the legs already, but we don't. So I don't think the circuit is happy, but let's just put some power supply FETs in just to double check, because these 640Ns are just old sacrificial ones anyway, so it doesn't really matter if we kill them. It'd be quite cool actually if this is like a bit in depth. It's always good when we have a repair on the live stream that's a bit in depth. It's a bit more than just FET skates, drivers, etc. So, like I said, I don't really have particularly high hopes for this working at all, based on what I've seen so far. But let's just see what happens. On the speaker terminal, we've got a full rail by the looks of it. On two of the, yeah, we've got full DC offset. So yeah, on the speaker terminals, we've got full DC on the speaker terminal. So yeah, there's definitely an issue here. So on the positive speaker terminal, we've got rail voltage. and on the negative speaker terminal we've got nothing. So yeah, there's definitely the drive circuit. It appears to be somewhat fucked. So I'm going to put the blame, I think, onto the 4427 there. Actually, I think that is misbehaving. That is the thing that is directly driving the MOSFETs. So if we've checked all of these transistors around the edge here, these all seem to be reading okay, no shorts or anything like that. So I think that our first point of blame is probably going to be the 4427. Yeah, let's pull that off the board to start with and go from there. Oh, I love it when we have drive circuit issues. It's good fun. Makes for a more interesting repair. There we go. Okay, so with that chip removed, we want to see what the voltages are on the pads that this chip goes into. We should really have some pulses perhaps on pins, I think it's 2 and 4, input A and input B, pin 2 and 4. On pin 2, which is one of the inputs, we actually have 4.5 volts, and on pin 4, which is another input, we have nothing. So we do have DC there, which kind of would want to turn on the low side of one side fully, which is a bit strange. Pin 7, which is supposed to be our VDD, we have 1.0. Now, why would that be the case? Too sure why that would be the case. Now, with that chip out, let's actually go ahead and probe the speaker terminals now and let the rail voltage build a little bit. We do still have DC on that speaker terminal, even with that driver removed. So maybe that driver itself there is actually fine. Oh, this is going to be a bit of a pain in the ass, I think. So I think we might be barking up the wrong tree with that driver. So I'm probably just going to resolder that down. I think we might potentially only have one of the auxiliary op-amp voltages, like, you know, plus minus 15. Say if we only had plus 15 and not minus 15, or in this case it might actually be plus 30, 15, 0 as the dual power supply voltages. If we only had one of them, then that might actually give us this kind of fault here where we've got DC on one of the inputs to this driver. So let's turn our attention then. What feeds that driver? What feeds that driver exactly? So we can follow some traces back from pins 2 and pins 4. If we look on the board here, we've got pins 2 and 4 going down here past this capacitor to a via just here under the board, which might jump over to here. Okay, looks like we've got an output of one of these chips over here. Now what I'm wondering is whether these chips are receiving their correct VCC, because if they're not, then we will get DC on these. In order for the amp to power up, this board has to sit on top of it. So we could use some risers. Then above the green we have white, and above the blue we have black. Okay, so that should now power on. 4.2 and a few of these. Interesting. So this looks like it has 4.6 on a bunch of its outputs, which I don't think is how that's supposed to be. We might have an issue there with the VCC generation circuit for this. See this MOSFET here? This MOSFET drives this little transformer, and that usually starts oscillating even before the MOSFETs, the power supply FETs, have begun oscillating. So let's see, does this begin to oscillate when the power supply FETs do? This will generate part of the VCC. Shit, it doesn't. It doesn't seem to ever start oscillating, this one. Okay. I'm starting to think whether there's an issue with whatever runs this MOSFET, because this MOSFET is not running, and that MOSFET should be running, and that creates VCC circuit components, VCC voltages for drive circuit, op amps, etc. Yeah, this MOSFET in the middle doesn't do anything, and it should be. But there's some op amps on the preamp board. Now this is one of the easiest kind of areas to see whether you have correct VCC voltage, etc. Because on the preamp board, op amps, you know for a fact that they will run on plus minus, you know, a voltage plus minus across the VCC, or you'll have like 30, 15, 0 across them. So let's check what we have across these op amps. So nothing there. And we only have 2.6 volts there. Yes, we are missing. We are missing VCC for like a huge part of the circuit here. This MOSFET should be switching from experience the moment that you apply the remote. So the FET itself is not shorted. So if we follow the gate of that FET, we can see what is supposed to drive it. So where does that go? Here we go. 470. We've got a 470 resistor there. And on the other side of that, where does that go? Does that go into this chip? Nope. Got a couple of transistors here. We go. Got a couple of little ZC. So that's the drive transistor. Here we go. Here's the pair of drive transistors for that little MOSFET. Okay, awesome. So that little single FET there, we've got a couple of drive transistors. That's ground, so that's the PNP. So the input then to these is going to be this leg, these legs here. So where does that go? That goes to this chip. So what exactly is this chip? Let's bring up a data sheet for this. Okay, VCC on pin 14. So what all this is just a it's an N OR gate. Is that an N channel OR gate? I can't remember this. It's like a set of 4 logic gates basically. So the outputs to the transistors that we are that we're missing PWM for are pins 10 and 13. So 10 and 13 are the outputs for the 3rd and 4th. You can see there, that's the outputs of these top 2 here. We firstly need to see whether we get any PWM on 8, 9, 11 and 12, and we also want to make sure that we've got VCC on pin 14. Provided we've got some signal on 8 or 9 or 11 or 12, well we need one for each, and provided we have VCC, then that we should get the PWM being passed through it correctly. But let's first of all check that we've got VCC pin 14. Okay, we have 5 volts on pin 14. VCC supply voltage, maximum is 7 volts, so yeah, that's correct. So, what do we have going in? So, pin 8, we have absolutely nothing. We have a tiny bit of DC. Pin 9, we have, we have 5 volts. 10, we have nothing. 11, we have nothing. 12, we have 5 volts. So we're not getting any pulses into this logic gate, set of logic gates. Fuck. So we're going to assume that the logic is supposed to be on pin 8 and maybe pin, so 8 doesn't have anything on it at the moment, and 11 doesn't have anything on it at the moment. Pin 9 and 12 both have the 5 volts. Okay, what feeds this chip with pulses? We've got a 555 timer. Glad you guys are all having fun. The 555 could be the driver. Yeah, let's see what's going into the 555 actually. Is the 555 actually outputting anything? Do we have VCC to the 555? We have 4.6 volts. Let's start with pin 1. Where's pin 1? Pin 1 down here. Nothing pin 1. Okay, pin 2 we have triangle wave, which is slightly DC offset into the positive. Pin 3 we have, aha! You know what? That is the first bit of PWM that I've seen on this fucking board, apart from the power supply FETs. So I wonder whether that actually eventually is supposed to go into the HC7402. And pin 4 we have 4.6, pin 5 we have 3.1, pin 6 we have triangle wave DC offset, pin 7, tiny little bit of PWM on the output of pin 7, and pin 8 we have DC. So let's just get a data sheet up of the 555 because I can't remember exactly what the pin out of that is. So VCC pin 8, okay. 1 is ground, that's correct. So trigger, we've got trigger and threshold, both have triangle wave on them, DC offset. Output is pin 3, which we do have PWM. 7 is discharge, which I can't remember what it does. Open collector output to discharge the timing capacitor. Okay, so that's fine. So the output, high current timer output signal. So yes, we do have output from the 555. That's fine. So where does that go? That goes into C527. Do we have anything else directly connected to pin 3? I don't think there. It doesn't look like there's anything else directly connected to pin 3. So maybe it could be C527 might be bad. If we have the PWM on one side of that capacitor but not on the other, that could actually be the problem. So we have PWM on that side. On the other side, we don't. Now, is that supposed to be there? That's interesting. We have a little bit of DC on the other side. I wonder whether that capacitor is bad, you know. The other side of the capacitor, where does that go to? Now, what's on the ZC? Do we have, if we have some DC on here, actually we've got a couple of pulses on here actually. Yeah, there are a couple of tiny pulses on the other side of this capacitor. So we got a couple of little pulses actually on here, on this transistor, this ZC. Now, is that supposed to go over to the... Hold on a minute. Hang on a minute. Aha! All of a sudden, ladies and gentlemen, we actually do have some PWM, albeit very janky looking, on this Mosfet that we didn't have at all day long. Now, what have I been doing? I've been touching my oscilloscope probe on that surface mount capacitor, haven't I? So I wonder whether this capacitor here is actually just kind of on its way out. Right, what do we have on the output MOSFETs now? Interestingly enough, what do we have on the output MOSFETs? If I now tell the amplifier to fully power up, what do we have on the output FETs? Holy shit! The amplifier now actually works. Okay, yeah, the output section now works. If I probe the output FETs, low side, see there on the scope screen, suddenly get output PWM. Wow, what an interesting turn of events. Now, I don't actually know the value of that capacitor, because although it seems to be like kind of working now, it does seem to be kind of working now, but I don't know whether I read it, whether it's going to be the right value. I don't know the value of that capacitor, so I don't really know what to replace it with. Naturally, we would want to replace that capacitor because it's temperamental. We've made it be working by just like touching it probably a couple of times. C527 there. This one right here. So I'm actually wondering whether a reflow, it doesn't look like there's much solder on it. I'm wondering whether the capacitor is actually fine and it's just it wasn't soldered correctly. There doesn't look like there was ever much solder on there. Oh my god, Zed, fuck me, what the hell, dude? 100 Australian dollars, that's about 60 fucking quid, mate. Holy shit, my dude. Thank you, Sam. And Prepare in Australia, thanks to you. Also, heating and cooling the capacitor here will actually also change its internal characteristics slightly. Like if the capacitor is starting to fail a little bit inside, heating and cooling it will change it slightly if it is failing. Let's power this board up with full rail now and confirm that we have stable switching on the low side FETs for both of the sides of the full bridge. Okay, we have 1.9 amps worth of idle current draw. We have switching on that side and switching on this side. Woohoo! That is a nice cheeky repair. I'm going to check the power supply FETs. See, that is a regulated power supply. If we go up in voltage, you can see there, regulation change. So that's maintaining a constant rail voltage. So yeah, this amplifier will now work fine and produce audio, all well and good. I could just prove that, or just quickly. Even though we've got we've got 640s in instead of 540s. But I could just whack in a little signal generator here into the RCAs. Nice. Efficient as well. It's proper kicking this woofer, and we only have 3 amps worth of current draw. That's awesome. Yeah, nice. I'm happy with that. That's a repair. We'll drop a new capacitor in there, even though it is working fine now. It could have just been needed reflowing, but I don't trust it, so I'm going to find out what capacitor it is and drop a new one in. But guys, hope you have enjoyed the stream. It's nice to actually get to the end of the stream and have a repair fully functional, rather than needing parts or needing looking at further. So I hope you enjoyed, hope you learned something, hope it was entertaining. Even if you weren't really paying attention to the repair, just kind of here for the vibes, I hope you were chilling, and I hope you had a great time anyway. I'm going to go and have a tasty hot chocolate, I think. Have a great one. See you all next time.